Hey, this is Hassan Haddad from section D1, and I will be performing a question from test 3. And this is the question, and this question focuses mainly on mapping and composite functions. And the most important parts of this question are listed out right here. This is the knowledge you need to know to determine whether these two functions are equivalent. And to determine whether they're equivalent, I'm going to start out by mapping this function. And if this function maps from a set to another set, this function must also equal the resulting set that this function maps to. And that sounds complex, but when I'm explaining it, it'll turn out to be pretty basic. I'm going to start out with the left side of the equation. So we're going to start out with T1. These are all linear transformations. Each function is a combination of transformations T1, T2, T3. And to begin, T1, this can be rewritten because these composite functions really mean these linear transformations are just functions of each linear transformation, and that'll be displayed in this. So T1, this can be rewritten as T1 Tx. This is just taking account of this. Eventually I will reach to what this entire function represents, but right now I'm just focusing on T1. So T1 maps from T1 takes in a vector of set V in set V and maps it into a vector in set W. So this is equal to so once you apply the transformation, you're going to get a vector in set W. But we're doing parentheses first because of PEMDAS, of course. So T2, T1. This is T1. This can be written as and T2 up here maps once you apply the transformation of T2, a vector in W is transformed into a vector in X. And as you can see, this is valid because T1 produces a vector in W. So T2, let me write that as. So it's going to be, push this out. And VW, as you will see in here at the top of the page, it's going to be transformed into. So right now you're mapping vectors. You mapped a vector in set V to a vector in set V, and so far this T3 has been excluded because we did parentheses first. And now we can rewrite this as and now T3, as you can see up here, T3 maps a vector in X to a vector in set Y. Therefore the mapping will turn out to look like this. And X is mapped to a vector. Once you apply the transformation, the vector in X is mapped to a vector in Y. And this is your left side of the equation. Now, for these to be equal, this mapping, this series of vectors that are being mapped into different sets of vectors has to be equivalent in this other function. And let's see if it is. So now I'm proving the right side of the equation. Start out with parentheses because they're in the equation. So we're going to begin with T2x. Okay. So T2x begins. T2, once you apply the transformation T2, a vector in set W is transformed to a vector in set X. So, as you can see, this is different from this step in the left equation, but we'll see if at the end we get the same thing. And then we're going to focus on this, the entire parentheses. So T3, T2 is really equal to T3, T2, X. Okay, and we go up here. T3 maps a vector in set X to a vector in set Y. And as you can see, this works very well because T2 maps a vector in set W to set X. So, using the mapping from over here, this is our initial, and then X is going to be mapped into a vector in set Y. And now, it's still not looking too equivalent, it looks pretty different. And now we're going to apply the last step, T3. And these dots, I didn't really say this at the beginning, they are composite functions. We've done as the function has said, we did parentheses first. And now, T1. This is equivalent to but that's the thing, because T1 is on the right side of the composite function. I actually did this incorrectly. So this is going to be equivalent to this. Because T1 is on the right side of the composite function, and you're compositing these two at first because they're in parentheses, T1 is going to be the most inner function. So you have, and what does T1 do? T1 maps, this will be valid if T1 produces a vector in a set W, because T3 composite T2 begins with a vector in W. Therefore, for this to even make sense, this T1x has to produce a vector in set W, and let's see if it does. T1, it takes a vector in set V, and once you apply the transformation of T1, it transforms into a vector in set W, and that is perfect. And once you take that, applying what we already did before, T2 transforms it to X, a vector in set X, and T3 transforms it to a vector in Y. And these are equivalent. So although these functions, each part of the function is done in a different order, they are equivalent, as you can see here. So the equations use the same combinations of linear transformations, just in different orders, and they produce one vector mapped into the final vector, and they are equivalent because the same vector is mapped into a new vector, v to y. And that concludes this question.